There's a lot of rounding steps in here where you may or may not round or round differently than what I've done up here. So as long as you show your work, then yeah, 35 is fine. Question? If there's a question, please ask. All right. Do number 5.
Where is it?
The 100 liters is your volume. The 1,000 grams, that's not N, but it's related to N. You can do a molar mass and convert that to N, right? N has got to be moles. Your Celsius has to be converted to Kelvin, but that will ultimately be your temperature, and you're solving toward pressure. So you know N and T and V, and you're solving toward T. The context of the ideal gas law is you will always know 3 of the 4 parameters. Are you getting what you should? Give or take a little for rounding. Yes? Maybe not. One thing. Volume's fine as it is. Yeah, you should be getting around 56 atmospheres. I got 55.988 something, 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 but that would round to 56.
Is the .0821 again only a
Yes.
question?
Question. If you're not getting that, please ask before we move on. All right. Problem number 6. What's different in problem 6 compared to all the ones we've done so far? We go through and label things. This is a temperature, this is a pressure. But you're asked about pressure and you're given another temperature, right? This is the first one we've had where there is a change of conditions. Ideal gas law was for a static set of conditions. You know, 3 of the 4 parameters. In this one, we've got changing conditions. And so this is where we're going to need what's called the combined gas law. Now, what I'm going to write on this side of the board, don't bother writing down. This is just an illustration of where the combined gas law has come from. But this equation, for whatever set of conditions you are currently at, this equation applies. And it relates those 4 variables at a single set of conditions. So for our starting conditions, the initial pressure, the initial volume, the initial amount, the initial temperature, all of that mathematically, if you lump all your variables together, all of that has to proportion out to R, right? Which is 0.0821. And any kind of change you make is going to cause another change so that it still maintains that equality. Now we normally write it PV equals nRT because that's a whole lot easier to type than a fraction. But if you lump all your variables together, this is what the equation would be. Are we okay with that? All right. So whatever these variables are, the ratio has to be 0.0821. And so what that means is, if you were to heat the sample and if you were to increase the temperature, then either volume is going to go up too, meaning the gas expands, or if the volume can't expand, it's going to build up pressure. The pressure would go up as a result of the temperature going up, or something like that, right? One cause changes another proportionate effect so that the ratio is still 0.0821. And so that means by the time we go in and we alter any of these variables to a new set of conditions, that new set of conditions still has to ratio out to R, correct? So your combined gas law is simply saying that if this equals this and this equals this, then this equals this. And you can set this set of conditions directly equal to this set of conditions. This part you write down. This is the formula for the combined gas law. Now the name combined gas law, if you flip through the book, they talk about Boyle's law and Charles' law and Avogadro's law and Gay-Lussac's law and a couple other folks' laws as independent laws. One of them deals with pressure and volume, one of them deals with pressure and temperature. I don't remember whose is whose, and that's okay. All right? Don't worry about those individual ones. All of those different laws are lumped together, combined into a single formula, which is your combined gas law. Combined gas law you need to memorize. That formula over there on the right you need to memorize. But the individual laws that you see in the book, like Bowles and Charles, etc., don't worry about those. Do you see that the combined gas law is really just the ideal gas law rearranged for before and after conditions? It's a rearrangement of PV equals nRT, where initial stuff equals final stuff, but they have to ratio out the same. All right, so then applying that to this question, 25 degrees is our initial temperature, 30,000 torr is our initial pressure, but we wind up at some different pressure and some different temperature. Whenever you have changing conditions, that's your cue to use the combined gas law. So, this is our formula. And we know temperature 1 and temperature 2. We know pressure 1, and we're solving for pressure 2. That still leaves us an awful lot of terms we don't have numbers for, correct? But when you read through that problem, is there anything said about the volume of the container changing? No. So let's just pretend for a moment that the volume is 200 milliliters. It'll cancel out, exactly. If the volume were 200 milliliters initially, but still 200 milliliters, then mathematically that drops out, correct? This is your list of variables, but in this particular problem, volume is not variable. In this particular problem, volume remains constant, and apparently so does the amount of gas. There's nothing said about CH4 leaving the container or anything like that, correct? You've got a temperature change that causes a pressure change. And so everything but the temperature and pressure components drops out as being constant. And so it simplifies down to this, in this particular instance. So then we can rearrange and solve for what we need to solve. We want pressure 2, so rearranging this equation to get pressure 2. It would be pressure 1 times temperature 2 over temperature 1. And then we plug in our terms. I'm getting 49.4 atmospheres. question about that? Is there a question?
How do you get the atmospheres? Is that just conversion?
Yeah, that's the 30,000 divided by 760.
So 760 is the base for atmosphere?
Yes, 760 torr is 1 atmosphere. That's a constant. Just think of that as just like any other conversion factor we've ever done, like 12 inches is a foot and so forth. That's a defined conversion factor. It is one that you need to memorize. Question? Do number 7. Just from reading this, do you see that this is a combined gas law problem, not an ideal gas law problem? By the information that you're given, that tells you. Combined gas law is for changing conditions. Ideal gas law is not. You got to have a way of showing that it's 3 significant figures. And so 8,880, if you just write it.
It's just
8,800. You got 3 significant figures, so this one counts, but that one doesn't. And so just writing 8,800 is ambiguous. So in this particular case, you wouldn't always have to do scientific notation, but in this particular number, you pretty much have to.
Why do you leave it in 4 instead of converting it to ATM?
I'm sorry, say that again.
Why do you leave it in 4 instead of converting it to ATM?
Well, I mean, you can do it in ATM. I mean, what would that be in ATM?
11.6. Yeah.
Okay. 11.6 ATM, yeah.
So you don't care what one is the other?
Well, the question doesn't ask for a certain unit, so either one of those is fine. I just converted back to torr out of habit. If I'm starting with torr, I try to give the answer in torr, but that's not a requirement. So 11.6 ATM is just as good. Plus that way you don't have to worry about being ambiguous with your significant figures. So that's a plus.
Since you don't have to worry about R, coefficient, constant, you won't have to even worry about converting at all if you want to go with the answer torque, right?
I was hoping nobody would ask that. But,
Because 760 would be a constant both sides at that point.
yeah, I mean, that is true. I mean, if we set this up, and we're solving for pressure 2, then we're not canceling units with R anymore. We're canceling units between this pressure and that pressure, right? This volume and that volume. That's not right. Volume to pressure to. And so, yeah, you're correct that you do have a situation here that if we plug in torr, we'll get out torr. And as long as these two volumes match, whether it's liters and liters, or milliliters and milliliters, or gallons and gallons, for that matter, it will work out. Okay? But the reason I was hoping to avoid that is you can shortcut all of these units on the combined gas law except temperature. You can't shortcut the temperature one that way. You're still locked into Kelvin. And the reason for that is you have to be using what's considered an absolute scale. And absolute scales are defined where the absolute minimum value is 0. In other words, no negative numbers allowed. Right? All volume, let's just start with volume. All volume units are absolute, meaning that 0 is the minimum volume, correct? You can never have -3 milliliters of something. That's just not physically possible, correct? So all volume scales are absolute. All pressure scales are absolute. Your amount is an absolute scale. It's either there or it's not being 0. You can't have -3 grams either, correct? That's not possible. But temperature scales are not all absolute. You can have negative Celsius, negative Fahrenheit stuff, correct? And so you can shortcut all of these units except the temperature ones. And you're still locked into Kelvin. Because Kelvin is your only absolute temperature scale. And now somebody on the exam is going to shortcut temperature and it's going to be all your fault.
I feel bad.
Question about that. It is perfectly legitimate to shortcut your units in the combined gas law for pressure, volume, and amount. And it will save you time. Question about that. That's a very good time-saving tool as long as you remember not to do it on temperature. Question on number 7. Anything at all on number 7? All right. Next comes Dalton's law of partial pressures. The context of this one is you're dealing with mixtures. There's more than one gas involved. So starting off here in the diagram, we've got 3 moles of the nitrogen, 1 mole of the oxygen. These are gas particles, so they're moving around randomly, colliding with each other, colliding with the container, bouncy, bounce, 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 all over the container. That's your motion. And every time one of those particles collides with the wall of the container, that generates pressure. Pressure is outward force caused by collisions of those particles with the walls. Now, in there, we've got 3 moles of nitrogen, 1 mole of oxygen. That means there are 4 total moles of, just generically, let's say, gas. And whether it's nitrogen or oxygen, they all contribute toward the pressure in the same way, because all gases behave the same, correct? So if we're trying to break out this total pressure, we're told there's 4 moles of gas and a total pressure of 10 atmospheres. Dalton's law is trying to break out that 10 atmospheres in terms of what part of that 10 is nitrogen pressure and what part of that 10 is oxygen pressure. And it's basically just done by ratios, or percentages if you want to think of it that way. The partial pressure of nitrogen in this mixture is defined as capital X here. This is a new unit for you. That's called mole fraction. It's equal to the mole fraction of nitrogen times the total pressure. Now, mole fraction for nitrogen would be its moles over the total moles. And 3 out of 4 is 0.75. Total pressure is 10 atmospheres. That means 7.5 of that 10 atmospheres is nitrogen pressure. Now, when you look through the book on the Dalton's Law section, the equations look a little intimidating and the definitions are a little awkward, but basically this is just percentages. If nitrogen makes up 3/4 of the gas, then it's going to generate 3/4 of the pressure. 3 out of 4 particles is a nitrogen molecule, therefore you could think of that as being that mixture as 75% nitrogen, correct? But it's not called mole percent, it's called mole fraction, and you leave it in decimal form, right? Because a long time ago, we said that percents in chemistry always mean based on mass. What portion of the mass is a certain element? This is not mass, this is moles. And so they very deliberately do not multiply it by 100, because then it could be mistaken for a mass percent when it's really a mole relationship, not a mass relationship, all right? But if we did multiply by 100, that would be a percent. Dalton's law is percentages. And you've been doing percentages for a very long time in math, probably middle school, right? This is no different, except you've got to make sure that you do your percentages, so to speak, in moles. If you're given gram data, you convert them to moles. You've got to set up that mole fraction in mole units. Right. Now, the partial pressure of oxygen would be the mole fraction of oxygen times the total pressure. 1 mole of oxygen out of every 4 moles of gas. Total pressure 10 atmospheres. The mole fraction of oxygen is 0.25. That means there's 2.5 atmospheres of oxygen, correct? Yes.
Why not just subtract 75?
That's the shorter way to do it, you're right. As long as there's only 2 components, right? But yeah, once you figure out that 7.5 of that 10 is nitrogen, then that pretty much implies the rest of it's oxygen, right? As long as nitrogen and oxygen are all you have, then that's correct. It works exactly like percentages do. And we didn't even have to calculate this 0.25 mole fraction because percentages have to add up to 100, correct? Just like percentages add up to 100, mole fractions always add up to 1. So I'm going to put the formulas over here for Dalton's law. Mole fraction for just some gas, generically I'm going to use the letter A. mole fraction for any particular gas is the moles of that gas over the total. The pressure for that particular gas is its mole fraction times the total pressure. The sum of all the mole fractions for however many items you've got has to come out to be 1. And the sum of all the individual pressures has to come out to be the total pressure. Now, when you phrase it like that, it looks nothing like percentages. You see what I mean by the actual equations look somewhat intimidating and hard to remember. But as long as you think of it and treat it as percentages, then you really don't need all those strict definition formulas. You work it like a percent. But you make sure you're in mole units when you do it. Question? Problem number 9. Oops, 9. We've got a container that has 50 grams of sulfur dioxide, 50 grams of sulfur trioxide, and the total pressure is 1,000 torr. And you're asked to determine the partial pressure of each gas. If the total pressure is 1,000 torr, you're splitting that up into how much is SO2, how much is SO3. And then since you're given equal quantities of them, it's awfully tempting to say that's a 50-50 mixture, half and half mixture, that's 500 torr each. But that's wrong. Why is that wrong?
1, 2, 3.
Because SO3 is heavier than SO2. And by the time you convert those into moles, those are not going to be equal quantities anymore, correct? $50 grams SO2 convert that to moles.